Assalamu alaikum. Hello everyone. This is our ninth class of CS224 and today's goals are gonna be about single precision and double precision. So let's get started. So basically before I just go and explain how to solve single precision and double precision problems, I need to explain that the computer doesn't understand numbers on its own. So especially floating numbers, as you can see here, floating numbers. So the computer takes the floating numbers and it changes to machine code in order to understanding like any other code. And therefore single precision and double precision are very important, and their structure is made, and they are made of three stuff in their structure. S stands for the sign, whether it's positive or negative, the number, right? For example, if I want to have plus 9, this plus is the sign bit, as you can see here. Okay, and the exponent is fixed for single precision, and it's 127. 127 is equal to 70f in hexadecimal, and 1023 is in decimal. I don't remember I think it's 7AA, but like I'm not sure yet, so I need to revise. And then the fraction, which is the mantissa, but that's all for now. I'm gonna explain how to solve it now. Here is a better structure in order if you didn't understand the previous time. Here is a better instruction. So the sign is 0 if the number is positive. Let's say 1 plus 101. So this is a number and it's positive. So the sign the sign is 1 bit and it's gonna be 0. And the exponent, it's always standard for single precision to be 70f, which is 127 in decimal. And the mantissa, which is, let's say, 0.0001, and anything after the decimal is the mantissa, which is going to be this number. So after understanding the structure, let's just get to one of the examples. Okay, so now it asks me to change this floating number, which is 9.0, to a single precision. Basically, normally we take the decimal number and we change into hex number, and from hex we change to binary. But since this binary number is so easy to change, this decimal number is so easy to change, I'm just gonna change it to binary, and it's very simple. 9 is 1001, and as you can see, point, and then the 0 is gonna be made of 4 bits of 0, and yep, this is my number in binary. As you can see, I said earlier, we changed the decimal number to hex and then binary, but since this number is pretty easy and simple, we don't need to go through all of these steps. Okay, so it says number 1, change given number to binary number, and as you can see, 9 is 1001.0000. Now, take the power from the scientific notation with its sign and add it to the exponent. Okay, this is sound kind of weird, but it's pretty simple and easy. I'm just gonna take this number, which is this whole number, and I'm just gonna write it in the best single notation, scientific notation. So 1001 is gonna be 1.001 times 2. The base is 2 because it's a binary number, power 3, right? So wait, let me write the 3 in a different color. You take this 3 and then you add it to the exponent. And remember, the exponent for single precision is 70f, right? So 70f plus 3, or I'm just gonna write 127. 127 plus 3 is 130. And if you change 130 from decimal to hexa, it's gonna be equal to 82. Well, that's everything for now. That's everything we need to do. Now we're gonna decode what we have got. So our number is positive. So our number is positive. So remember, the structure of a single precision is a sign, exponent, and the mantissa. And the sign, I forgot to tell you that this is gonna be our mantissa, 0001. Let's go back. So the sign is positive. The sign is positive for 9 and it is 0. So I'm just gonna write 0 in the first bit. And the exponent is not gonna be 70f. The exponent is gonna be 70f plus the power we took from the scientific notation, which is going to be 82. And I'm just going to break this to 1, 0, 0, 0, and 0, 0, 1, 0. So the 8 is 1, 0, 0, 0, and the 2 is 0, 0, 1, 0. And then the mantissa, which is gonna be 001. But remember, the mantissa is made of 23 bits, and I only have 3 bits here. So basically, I'm just gonna write 001, and the rest of the, so 23 minus 3 is 20, so the rest, which is 20 bits left, are just gonna be a lot of zeros till we just get like 20 zeros from here to here. So now let me decode what we have got. So we said the number is positive, so the sign is 0, and then we said that we have the exponent, and my new exponent is this number, right? Is this number? Oops, is this number? So I'm just gonna take it and add it here. Oh my god, so sorry about this. 1 0 0 0, this is 8, and 0 0 1 0, this is 2. And now the mantissa, which is 001, and I'm just gonna need to add a lot of zeros till the total number of bits becomes 32. So I'm just gonna pause here and come back when it's done. Okay, now let me just recap. This is gonna be the sign. These 8 bits are gonna be the exponent, right? 1 2 3 4 5 6 7 8, and all of this is gonna be the mantissa, and they're in total 32 bits. So the difference between, like, one of the differences between single precision and double precision, that single precision is 32 bits, but double precision is 64 bits, which is 32 multiplied by 2. Therefore it's called double precision. I think it's easy and clear. Well, next step is to break this down to nibbles. So the first 4 bits gives me 4, and the second 4 bits gives me, the second 4 bits gives me 1, and the third 4 bits gives me another 1. As you can see, I have 0 0 0 0 0, and they should be total of 8 nibbles. So 1 2 3 4 5 6 7 8. Yep, and this is my final answer. So I changed, as you can see here, I changed the floating number 9.0 to 0x4110000000. I think. Oh, there is an extra 0. And this is the machine code for single precision. Now let's go the opposite and see if this actually gives me 9 or not. Okay, as you can see here, we just proved that 0x41100000 is equal to 9.0, and now we just want to go from here to here, which is like the opposite. So basically, first step, you're gonna break the code, which is the machine code. You're gonna break it to set of binaries, right? So as you can see, I broke it here. Like every bit is looking for its broken parts. Next step, you need to get this, which is the table, the structure of a single precision. You need to take it and then break it down. So we said the first bit, and this is the first bit. And now for the next 8 bits, which is 1 2 3 4 5 6 7 8, and these are going to be the exponent. And as you can see here, all of this is going to be the mantissa, and that's it. Okay, so we said that positive, if the first bit is 0, then the number is positive, and therefore our number is positive right now. Okay, and then we take the exponent. We have our exponent as this is 8. Wait, with a different color, with another different color, Magneta. So this is 8, right? 8, and this is gonna be 2. So my exponent now is 82. Okay, next step, when you take the exponent, you minus it from the original exponent. And remember, the original exponent for single precision is 70f. Let me write it with a different color. So 82 minus 70f gives me 3. Also, you can write this as 130 minus 127, and it's gonna give you 3 as well. Okay, next, and you need to put this as a ring in your ear because it's very important. When you take the mantissa, before you take the mantissa and write it down or like break it down, you need to write 1 point anywhere, just write 1 point, and then take your whole mantissa, which is all these numbers. Oops, which is all these numbers basically, without this and without this line. You take it and you're just gonna put it here after the dots. So what do you need to do? Remember, when you break the mantissa, always add 1 point and then take the mantissa, which is 0. Wait, with a different color, or let's say original color. 0, 0, 1, and then all of them are gonna be zeros, which is like zeros extension. So I won't care about this. I'm just gonna leave it as it is now. Okay. After this, you're gonna take your number to the last one, and the last one here is this one. So I'm just gonna write 1.001 times 2, because the base is 2. And what is the power? Well, the power is what we have figured out from the exponent, which is power 3. We're just gonna write it here, right, with a different color as well. 2 power 3. And this means the dot is gonna move 3 to the right, 1, 2, 3, which is gonna give me 1001, and 1001 is a binary number. If I change it to decimal number, it's gonna give me 9.0, and therefore this is how to get 9.0. Now let's move to harder example to explain it way better. So now I have 80.5 as a decimal number, and I want to change it to a single precision machine code. And remember what we said. The first step is to change your decimal number to binary number. But this is gonna be a lot of work, so I'm gonna change it from decimal to hexa and from hexa to binary. So 80, I hate this color. Let's take this one. 80 is my decimal number, and I want to change it to hexa, so I'm gonna divide it by 16, right? As I said in the previous video, you take the number divided by 16, and it's gonna give me 5 as the result. And what is the remainder? The remainder is 0. Next, you take this 5 and you divide it again over 16, which is gonna give you, 0 as an answer, and remainder is 5. Next, you take this number and you write it from down to up, from bottom to up. Yes, to top, from bottom to top, and you're gonna get 50. So this is my hexa number, my full hexa number. So 80 becomes 50. And now I'm gonna change this 0.5 to hexa number as well. Let's change the color. Oops, oh, yeah. So 0.5 times 16 is gonna give me 8.0, and when your decimal part is 0, you stop, and this is gonna be my decimal number in the hexadecimal number, so it's gonna be 50.8, and this is the first step. Now I'm gonna remove everything and come back. Okay, so this is my decimal number and this is my hexadecimal number. I'm gonna change my hexadecimal number to binary, and it's pretty simple and easy, right? So 5 is gonna be 0, 1, 0, 1, and 0 is gonna be 0, 0, 0, 0, and then another point, because remember the decimal goes here, and then 8, which is gonna be 1, 0, 0, 0. So let me write it in a better way and come. Okay, as you can see, this decimal number changed to hexadecimal number, and this hexadecimal number changed to binary number, and now we can start working. First, we know that the number is positive, so the sign is gonna be 0, right? And what do we need to do now? We need to change this number to scientific notation in order to see our new exponent. And basically how to change this, I'm gonna move this dot to the first one, which is this one. So it's gonna be with a different color. Let's take violet. 1, 2, 3, 4, 5, 6. So right now I'm gonna write my new number as 0, 1, You know what? No need for 0. 1.010000, there are 4 zeros, right? Yes. 1 times 2 power 6. And it's the same number, right? All I just did is write it in a scientific notation, but this mathematical equation looks bad. So I'm just gonna write times 2 power 6, right? You take this 6 and you add it to the original exponent of single precision, which is 70f. 70f equals to 127 plus 6 is gonna give you 133, and 133 in hexadecimal is 85, and now 85 is made of 10000101. And remember, this is our mantissa. Yeah, you can't forget the mantissa. It's very important. Mantissa. Okay, I think now we're ready to solve. Okay, so we said we said that the structure of single precision is made of three stuff: sine, exponent, and mantissa, right? What is the sign? The sign is 0 because the number is positive, as I said earlier. Next, we're gonna write the new exponent, which is 8 with a different color, which is 85, and 85 is made of 88 is made of 1000, and 5 is made of 0101, and then we are just gonna write the new mantissa, which is this part, and it should be equal to 32 bits overall. So it's gonna be 01000001. I hope I didn't miss anything. Yes. And then just a bunch of zeros till all over bits are 32 bits. Okay, and then we're gonna end up with these with these 32 bits. Now it's time to break them down. This is gonna be 4, and this is gonna be 2, and this is gonna be 1, 2, 4, 8. 8 plus 2 is 10. This is gonna be A, and this is gonna be 1. This is gonna be 0, 0, 0, 0. So my final answer is gonna be 0x4 1a2 0, 0, 0. 0, I think. 42a1 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 0, 0, 0, 0, 0, 0, 0. And yep, this is how to change 80.5 from normal decimal to single precision. And now I wanna make the opposite of this one, which is showing what is the number. Like, this is our decision, this is our machine code, and I want to show it in a single precision number, in a number. I want to show it in a number, in a decimal number. So I'm just gonna do it right now. So remember, first step is to break all the machine code is to break the machine code into set of binary numbers, and that's what I'm gonna do. As you can see, all of this is equal to this, but they're not looking cool. Well, they do look cool, but yes. So this is the machine code, and this is the binary of the machine code, the binary number. Okay, now I have the table. I will do it again. I will say it again one more time. So basically, my machine code is made of these 32 binary bits. The sign is 0, which means the number is positive, and I got these exponents, which are made of 8 bits. 1, 2, 3, 4. 1, 2, 3, 4. Yes. And then the mantissa, which are these 23 bits, and this is the exponent. So my exponent is 1000 divided. So this 1000 is 8, and this 0101 is 5. So my exponent is 5 right now, 85, right? And remember, when we take the new exponent, we always minus it from the original exponent, which is 70f, and the difference should be 6, right? And now we got the sign, we got the exponent. Now it's time for the mantissa. Remember, as I said earlier, always write 1 point before you write your mantissa. And what is the mantissa? The mantissa is the number after the 85, which is this number. So basically, I'm just gonna copy all of these numbers, which is our 0, 1, 0, 0, 0, 0, 1, and then the rest are gonna be 0, but like they're just 0 extensions, so I don't care about them. I care about them when the number is repetitive, but the number is not repetitive right now. Okay, and they should be, and they should be times 2 power the difference of exponent, which is 2 power 6, which means this dot is gonna move 6 bits to the right, which is with a different color now. 1, 2, 3, 4, 5, 6, which is gonna give me, I'm just gonna write it down here with a text 1, 0, 1, 0, 0, 0, 0, dot 1, and then 0, 0, 0, 0, whatever it is, right? Okay, this is 1, this is 2, this is 4, this is 8, this is 16, 16, 32, 64. So 64 plus 16 gives me 80, right? 80? Yeah, it gives me 80. And what did we say? Okay, and then the rest are these 4 bits, which gives me 8, and this 8 goes here. So it's gonna be 80.8. I'm sorry. Remember when I said we need to change the number to hexa number, the decimal number, we need to change it to hexa number, then we change it to binary number, and I totally forgot about this. So I just moved this binary number from binary to decimal number, which is wrong. You basically need to change it to hexa number first. So this is gonna be 5, right? This is gonna be 0. These 4 bits are gonna be 0, and this is gonna be 5, right? And this is gonna be 8. 50.8, and then you change this 50.8 to decimal, and basically you just take 5 times 16 plus 0, 16 power 1 plus 0 times 16 power 0, which is gonna give you 80 plus 0, which is 80. And then I'm gonna take the decimal, which is 0.8 times 16, which is gonna give me, sorry, my bad, it's not times. I'm just gonna take 0.8, 0.8, so this is index number 0, and this is index number -1. So basically this is gonna be 8 times 16 power -1, which is gonna be 8 over 16, which is equal to 0.5, and you take this 0.5 and put it up here, right? So it's gonna be 80 point, okay, and then I have the decimal as 0.5 and I have the full number is 80, so it's gonna become 80.5. Sometimes I make these silly mistakes by forgetting that we changed the decimal number to hexa, and from hexa to binary, right? But what I did, I just took the decimal and I just took the binary number and immediately changed it to decimal number, which is wrong. I should have taken it as binary to hexa, and from hexa to decimal, as I just did here. So this binary changed to hexa, and this hexa changed to decimal, and therefore I was able to get 80.5, which is the same number we started with. 80.5, the same number we started with. We changed 85 to this machine code, and then we took this machine code and we changed it back to 80.5. And this is for single precision. I'm not going to start double precision in this video, maybe in the next video. See you and have a good day.